property of solving exponential and logarithm equations. For all real numbers b greater than 0 and a cannot be equal to 1, and any real numbers x and y, the following are true. If x is equal to y, then b to the power of x is equal to b to the power of y. So if we can make the base equal each other, we can conclude that the exponents are equal. In further example, you will see that where it's possible, we would make base, both sides of the equation, the same, and from there we conclude the exponents are equal and we solve for unknown. Number 2, if b to the power of x is equal to b to the power of y, if the base is the same, then exponents must be the same, then x must be equal to y. So we can conclude from b to the power of x is equal to b to the power of y. From there we can say, well, x must be equal to y. Number 3, if x is equal to y and both are positive, x is greater than 0, y is greater than 0, then the log of x must be equal to log of y with the same base. So from here, if I have an equation, it says log of x is equal to log of y, I can just conclude from that x is equal to y. I can just drop these logs and conclude that x must be equal to y and solve for unknown. And number 4, if x is greater than 0 and y is greater than 0, then log of x is equal to log of y. Then from there we can conclude x is equal to y. Notice that the base has to be the same. So let's take a look at some examples. We're going to solve the equation, approximate the solution in 3 decimal places. Here we have 10 to the power of x is equal to 4. If I can make the base the same, I can conclude the exponents are the same, but over here I can't. So I can take a log of both sides. From here I can say the log of 10 to the power of x must be equal to the log of 4. Okay, from here I'm looking for the exponents x here. Recall that I can move that x right front of log. One property that we learned, have log of x to the power of n. You can write this as n log of x. In this case, I can take this n and move it right front of the log. Move this n to the right front of the log. That's what we're doing here. We're taking this x here, move it right front of this log. So this becomes x log of 10. We want to isolate x. We're solving for x. So x must be equal to, if I divide both sides of the equation here by log of 10, it would be log of 4 over log of 10. So here I can use my calculator and we can find x is about 0.602. So the solution is 0.602, 602. Solve an exponential equation with base e. Solve e to the power of 0.02x is equal to 192. Approximate the solution to 3 decimal places. In this case, to solve for x, you have to take a natural log of both sides, ln of both sides. If I do that, I can use the property that I learned. If I have e to the power of 0.02x, if I have natural log of that, I can take this part here and move it right front of this natural log. So its exponents here, from here, I can take it, put it right front of that. Here we have equal to 0.02x times natural log of e. So that's the property we're using. So this exponent here goes right in front of this natural log. So we know that natural log of e is equal to just simply 1. Because that exponent is 1 here. The base is e, so that must be equal to 1. Just like we had before, if I had log of 10 is equal to 1. Remember that? Because why? Because exponent is 1, the base is the same as the exponent. So in general, if I have log of b, if the base is the same as exponents, whatever number here exponents is, that's what would be equal to, r. So as you see here, since the base are the same, so natural log of e would be equal to 1. Just like that here. log of b to the power of r is equal to r if the base are the same. Log of 10, remember, was equal to 1 because the exponent is 1, matching the base. So in this case, natural log of e would be equal to simply 1. So on the left-hand side, you get 0.02x is equal to natural log of 192. To solve for x, I divide both sides of the equation by 0.02. So I'm going to use my calculator here to obtain this result, 262.875. So the solution is in the brackets. You can write it as 262.875. Solve an exponential equation. We're going to solve 5 to the power of minus x plus 7 is equal to 9. So to do this, to solve for x, you need to take a log of both sides. So I can move these exponents right front of the log so I can solve for them. We call that log of a to the power of x. That's the same as x log of a. So this x right here can be moved right front of the log. That's exactly what we're doing here. Once you take a log of both sides, these exponents here can be moved right front of the log. Now I can distribute. I get minus x log of 5 minus x, that would be, and then 7 log of 5. Now I can distribute this, solving for x. All right, now we have minus x log of 5 plus 7 log of 5 is equal to log of 9. Remember, we're solving for x. The only terms contains x is this term here. I'm going to isolate this. So I'm going to subtract 7 log of x from both sides of the equation. That goes to the other side then. Now the coefficient of x is minus log of 5. If I divide both sides by minus log of 5, this would be my x. To calculate this, we need to use our calculator to solve, and the solution set is 5.635. So general method for solving an exponential equation: take logarithm to the same base on both sides, and then use the power rule of logarithm, or the special property log of b to the power of x would be equal to x if the base is the same as b. There's a special case if both sides can be written as exponentials with the same base. You do that, you do so, and set the exponents equal. Solve equations involving logarithm. We're going to solve log of 3x plus 2 is equal to 3 with the base 5. What we need to do in this case is to use the property that we had before, where log of x is equal to y with the base b. We should be able to convert this to this exponential form. So that would be the base of the logarithm would be the same as the base of the exponential. So b to the power of y would be equal to x. That's how you can go back and forth with this. But in this case, we're going to take this here and convert it into its exponential form. As you see here, the base of the log is 5. So we write 5 to the power of 3 here. 5 to the power of 3, just like what you have here, b to the power of y. 5 to the power of 3 must be equal to, but in this case my x is 3x plus 2. So 5 to the power of 3 is equal to 3x plus 2, or 3x plus 2 is equal to 5 to the power of 3. By doing this, you don't have any log here. That's all we have to do here is to solve for x, isolate x. 5 cubed is 125. To isolate x, I'm going to subtract 2 from both sides of the equation. That becomes 123. Divide both sides of the equation by 3. There it is, 41. Check to see the log of 3 times 41 plus 2 is equal to 3. It's true. So the solution is 41. Solve a log logarithmic equation. We have solve log of x plus 1 to the power of 5 is equal to 3 to the base 3. So to do this, we need to convert the logarithm into its exponential form. Here, if I have log of x is equal to y to the base b, that's the same as b to the power of y is equal to x. So in this case, my base is 3. So it would be 3 to the power of 3 is equal to all these stuff that we have here, x plus 1 to the power of 5. So this is my x, really. My base is 3, and my y is also 3. So it would be 3 to the power of 3 is equal to x plus 1 to the power of 5, or x plus 1 to the power of 5 is equal to 3 to the power of 3. 3 to the power of 3 is equal to 27. X plus 1 to the power of 5. In order to solve for x, I need to eliminate this exponent's 5. If I raise both of these sides to the power of 1 over 5, then I can reduce this 5, or take a fifth root of that. So if I raise both sides of this equation to the power of 1 over 5, that 1 over 5 and 5 reduces to 1. This would be 1 over 5. So remember, 27 to the power of 1 over 5 is a fifth root of 27. We call nth root of a to the power of m the same as a to the power of m over n. So we have x plus 1 is equal to the fifth root of 27. So if I subtract x from both sides of the equation, x would be equal to minus 1 plus fifth root of 27. We can check our answer easily, substituting for each x value that we found. And we see that it's true. 27 will equal to 27. Here we're going to solve this equation here. The left-hand side, I have log of 2x plus 5 plus log of 3. Looks like I can combine these two using one of the property that I learned, that log of x plus log of y would be equal to log of x times y. I can combine them. Remember, the base has to be the same for all of them. So in this case, as you see, the base is 8, the same. So log of 2x plus 5 plus log of 3 can be combined to log of 3 times 2x plus 5. I can combine these into one logarithm. Because from here, I can conclude that if log of x is equal to log of y, if the base are the same, from here I can conclude that x must be equal to y then. That's exactly what we're doing here. We're saying that if log of something is equal to log of something else, the base are the same, then in this case 3 times x plus 5 must be equal to 33. So I don't have any log anymore here, so I can solve for x. And to do this, we can distribute, or we can divide both sides of the equation by 3, so I don't have to deal with this large number. If I divide both sides of the equation by 3, on the right hand side I get 11, then I get 2x plus 5. To solve for x, I subtract 5 from both sides of the equation and divide both sides of the equation by 2. Then I would get x equal to 3. You can check our answer by substituting for each x 3 and conclude that the solution set is 3. Here we're solving this equation for x. In the left-hand side, we have log of x plus log of x plus 15. So I can combine these two using the fact that log of x plus log of y is equal to log of x times y, knowing the base are the same. So in this case, I have log of x plus log of x plus 15. I can write it as log of x times x plus 15. I'm combining this into a single log. So at this point here, I can rewrite this as its exponential form. We call that log of x equal to y. I can write this as, if the base is b, it would be b to the power of y is equal to x. So to drop this log here, I need to convert this to this exponential form. That's exactly what we're doing here. The base here is 10. So if there's no number here, it means it's 10. So there we have 10 to the power of 2 is equal to x times x plus 15. So x plus 15 is equal to 10 squared over 100. And distribute the x, I get the second order equation, x squared plus 15x. If I move the 100 to the left by subtracting 100 from both sides of the equation, here I get the x squared plus 15x minus 100 is equal to 0. We can either factor this or use quadratic formula. Looks like it's factorable. 20 and 5 would be the product of 100, and if I have plus 20 minus 5, that would be sum of 15. If you still have a problem with factoring, please refer to my lectures on factoring. And once you do that, then we can set each of these parentheses equal to 0. We get x plus 20 equal to 0, so x equal to negative 20 and x equal to 5. Now, the value negative 20 must be rejected as a solution, since it leads to the logarithm of a negative number in the original equation. So the only solution we have is 5. Solving a logarithmic equation. Step number 1, transfer the equation so that a single logarithm appears on one side. We're going to use our properties that we learned. Use a product or quotient to combine them into a single logarithm. Use the product rule or quotient rule or logarithmic to do this. Step number 2 is to do one of the following. Either use this property here. If log of x is equal to log of y with the same base, you can conclude that x is equal to y. Or you have to sometimes write this in its exponential form. If I get log of x equal to k with the same base b, that would write it as b to the power of k is equal to x. Then we can solve for x.